Welcome everyone to the Saskatchewan Science Centre. My name is Sandy Baumgartner and I'm the Chief Executive Officer, a girl with a big title, and lots of people to help me do lots of cool things. So I want to thank you all for coming today. I think you're all from Argyle School, so you know why you're here. Thank you very much for coming. We look forward to hearing a bit about some of the things that you're doing. I get to introduce our speaker today, Stephen Hall, and he gave me permission to say whatever I like about him, so here it goes. Actually, the fun thing about Stephen is Stephen used to be me, or he's the old me. Stephen worked here at the very beginning of the Science Centre back in the late 80s, 1980s, if none of you were around then, maybe your teacher might have been. And he was responsible for a lot of the exhibits that we still have here at the Science Centre. So I think it's pretty cool to have him here again to talk to you about some of the things that he's been doing since he left here, whenever it was that he left, I'm not sure. But it was long before I came here. And Stephen originally came from the Ontario Science Centre, so he knows and understands science centres pretty well. So if you've ever come here and had a good time, particularly with things like the bubbles and the hot air balloon, you have this guy to thank, because he's the one that created the vision for this place that we can all come and enjoy for the rest of our time. He also will tell you a little bit about a royal tour. He was here on the official opening day, and there was some celebrity royals here to officially open the Science Centre, so he's got a lot of good stories. But that's not why he's here today. Through his career, he's done a lot of work in various things in terms of advertising, television, but he has a personal interest and a strong affinity for all things in the environment, and he's put together a special presentation for you guys today about the environment, about conservation, and a little bit about climate change to sort of inspire all the students here in the theater, but also those at home that are watching in their classrooms to do things for energy conservation and for the environment now and into the future. I'm not sure what the lamps are about, maybe to give the feel that we're in Stephen's living room, but sit back, listen. I think he's got an entertaining talk for us today, and make sure you've got lots of questions, because I know that he likes to take your questions. Before he starts, I just want to thank some of our partners and sponsors. The Saskatchewan Environmental Society is here. We've got cooperators here, and we've got Sarcan here. All the people that behind the scenes are making the 25 Acts of Conservation contest happen. So thank you very much to our partners and sponsors, and we'll hear more about them later. And I'm going to turn it over to Stephen. So thank you all for coming, and off you go.
Thanks, Sandy. So actually, the lamps are from my living room, and I'll get into that in a little while. And by the way, the Royal Tour happened, a long time ago, 26 or 27 years ago. It was supposed to be about 45 minutes long, and it was only 8 minutes long. So when I was doing Sandy's job, I used to say, I'd give you the Royal Tour, but it's only 8 minutes long. This tour is going to be a little bit longer than that. I'm going to talk about thinking differently about energy, but before I do, I just want to encourage all of you to participate in the 25 Acts of Energy Conservation. It's easy to do. So you can register your school at the Saskatchewan Environmental Society's website. And then it's just a matter of doing a few things. You want to pick an energy conservation action, something that you can do to conserve energy or conserve water. Think of a creative way to show it. And then take a picture or video of you actually doing it, actually making a difference, conserving energy or water in some way, and send it in. And it'll be fun. And I think there are prizes. So yeah, you should get out and do that. And while you're doing that, while you're thinking about that, thinking about participating in the 25 Acts of Energy Conservation, I want to encourage you to do this. I want you to think a bit differently about energy. And that's what I want to be doing today. I want to be talking about that. I want to start with a little exercise. And so I'm going to start with everyone on the left side of the room. Okay, so everyone this side of the projector. When I say, I want you to say a word. Okay, I'll count down. So I want you all to say it out loud, one word. Okay, you ready? 3, 2, 1.
Energy.
Okay, one more time.
Energy.
Very good. Okay, you guys can relax. Now, everyone on this side of the room, on the right side of the room, that side of the projector, I want you to spell this next word. Okay, so don't say the word, spell it. Okay, and 3, 2, 1. Okay, let's do it a bit faster. 3, 2, 1.
Energy.
Again, faster still.
Energy.
Okay, now everyone together.
Energy.
Excellent. Well, that's kind of our little warm-up exercise. And I wanted to show that we can use different techniques, but we can get the same result. Okay, on this side, we said energy, which is a 6-letter word. Okay, so we used 6 units, and we said energy, and it sounded like energy. On this side, we used 3 letters, 3 units, and it still sounded like energy. So energy, energy, it sounded the same. Different techniques to get the same result. I want to talk a little bit about that today. Take a look at these lamps. You see any difference? They're the same shape, the same style, they're pretty much the same. They're from my living room, and we picked them to match, so they're meant to look the same. And they're the same brightness as well. But they're actually different. They're different. They're the same brightness, which is 450 lumens each. I'm not sure if any of you have heard that term before, lumens. A lumen is a measure of light. So they're both creating the same amount of light, 450 lumens. Okay? Let's talk about how we measure things. So we measure length in meters. We measure weight in grams. We measure light in lumens. Who knows what we measure electricity in? Watts. Very good. We measure electricity in watts. And when we think of light bulbs, oftentimes we think of light bulbs in terms of watts. We haven't actually typically chosen light bulbs for their light level. We normally say, oh, I need a 40-watt light bulb. And if we did get a 40-watt light bulb, that would be 450 lumens. Okay? A 60-watt light bulb, a little bit brighter, that's 800 lumens. A 100-watt light bulb, pretty bright, that's 1600 lumens. Well, let's get back to these lights for a second. So these lights are the same brightness, but they're different. They're using the same, different techniques to get the same result, just like our energy little exercise. But as you probably guessed, this one's an incandescent, and that one is an LED. They're both producing 450 lumens of light each, but they're different. Well, actually, maybe this is the LED, and that's the incandescent. I'm not sure which is which, actually. How can we find out? They're both producing same amount of light. They both look the same. How can we find out which is which? Obviously, we could take a look at the bulbs, right? We could go in and look and take a look because the bulbs look a bit different. Is there another way? What if we found out how much electricity they use? Okay. What if we measured how much electricity is powering that one and how much electricity is powering this one? Well, that's what we're going to do. And to do this, we're going to use a watt meter. Now, this is a watt meter. It's pretty cheap. Actually, you can buy one of these for about 20 bucks. And we're going to check how much light each of these lamps is using by checking the number of watts. Okay, remember, this is how we measure electricity using watts. So let's do the test. I'm going to plug this watt meter in. Make sure it's working. Okay, so the first thing I'm going to do is unplug this one here and plug it into the watt meter. And I'm going to need some help. We have a volunteer from here. Someone come up. People are shoving each other. So what does that say?
40.7.
40.7. 40.7 watts. Okay, so hang tough there. Stay there for a second. So now we'll plug in that one. And what does that say?
5.7 and 5.5.
5.5, 5.6. 5.5, 5.6 watts. Okay, thank you very much. Okay, so this one on this side was using just over 40 watts of electricity. On that side was using just over 5 watts of electricity. So which is which? This side is incandescent. Incandescent. That's the one that's using up all that power. Well, let's do this. Let's take a look at the incandescent light bulb. Okay? This light bulb has been around for a very long time. Okay, it's been used for many, many years. And I want to talk about how it works, because it kind of works in an interesting way. It uses this thing here called a filament. And the interesting thing about a filament is filaments do not like having electricity go through them. They're what we call a poor conductor of electricity. So when we put electricity through it, so we put electricity and it flows into the light bulb, that filament resists the flow of electricity. It hates having electricity go through. I don't want to do it, I don't want to do it. And all that resistance creates heat. Okay, so the filament heats up. And eventually it heats up so much, it gets so hot that it begins to glow. Okay, and this is finally how we get light. So we put electricity through it. The filament, lousy conductor of electricity, so much so that it heats up and glows, and finally we get some light. Let's look at this in the form of a schematic. Okay, so we've got electric energy going in. We get the light energy. That's the useful energy. That's what we want. That's why you turn a light on, right? That's why we call it a light. Turn the light on. I need light. I want to read, or I want to light up the room. And that's fine. That's useful energy. But look how much energy gets lost to heat. Okay, we're generating heat. We don't want heat. We want light. Okay, let's look at an LED light bulb. It produces light in a completely different way. Just like the other light bulb, electricity flows in, but this time, instead of creating heat, the LED, which is a light-emitting diode, the electricity enters and causes some electrons, tiny units of electrical energy, to move, and as they do, they emit photons, which is light. So it's pretty straightforward. Electricity flows in, the LEDs emit light, and there's a little bit of residual heat. Let's look at the schematic for that one. Again, electrical energy comes in. We get the useful part, okay, the light energy, and there's a little bit of waste here. What's really interesting is, look at this useful light energy between the LED and now the incandescent. LED, incandescent, it's exactly the same, right? Both of these are producing 450 lumens of light, so the amount of light energy we get out of them is about the same. But the heat energy that's wasted in the incandescent is about 90% of the electrical energy going in, okay? Interestingly, there's another appliance that we have in our homes, most people have in their homes, that has the same kind of energy schematic, okay? There's a lot of heat energy created, but this time it's actually put to use. We want heat, okay? Plus we get a little bit of light energy. Can anyone guess what that appliance is? I'll give you a hint. It also has a filament. So it also has a piece of wire that really hates having electricity go through it, so much so that it heats up and creates heat, and there's a little bit of light. Can anyone guess what it is? Yeah, some stoves do work this way. Actually, I was thinking of the toaster. Okay? Toaster works pretty much exactly the same way as a light bulb. Okay? There are filaments, and they resist the flow of electricity. As a result, they heat up, and they also generate a little bit of light. So exactly the same flow as the light bulb. Electricity flows in, heats up those filaments, and there's a little bit of residual light. So the incandescent light bulb is pretty much done. Okay? In fact, there's been government regulations. They're not even making them anymore because they're so inefficient. All right? So we say bye-bye to the incandescent light bulb. There's still a few kicking around. We'll talk a little bit about that in a moment. But when you think of an incandescent light bulb, I want you to think of this. It's good for toasting bread. Not so much for making light. Okay? We have way better technology for creating light now. So I want to leave this part of the presentation with a little conservation action. Okay? Go back to your homes, look around for those incandescent light bulbs, and get rid of them. Swap them out for LED. Okay? Okay, why should we care about this? I mean, why? Really, we get the same amount of light. Okay? Really, it doesn't matter. You got to hook up a light meter to even tell which is which. Why should I care? Well, there are two reasons that I want to talk about today. Reason number one is this. Power is not free. It is not free. Okay? When you go home tonight, I want you to ask your parents to dig up their SAS Power bill, or maybe go online and see your bill online. And when you do, I want you to look at that bill and look at this line and look for something called the cost of electricity. Okay, look really closely at that, and you'll see that in Saskatchewan, in Regina, the cost of electricity is about 12.6 cents a kilowatt hour. It actually says it here, it's $0.12623 per kilowatt hour, which is about 12.6 cents per kilowatt hour. So it's not free. A kilowatt hour is a measure of electrical energy. So let's review the sort of the way we measure things again. So we measure kilometers, we measure length in kilometers, we measure weight in kilograms, we measure light in kilolumens rather. We measure electricity in kilowatts, and electrical energy in kilowatt hours. So a kilowatt hour is actually not that complicated, really. It's the amount of electricity times the amount of time we're using it. So a kilowatt hour, let's say we have a 100-watt light bulb and we have it running for 10 hours. We'll have 1,000 watt hours, or 1 kilowatt hour. And that kilowatt hour will cost you about 12.6 cents. In Saskatchewan, the average home uses about 750 kilowatt hours of electrical energy every month. And that's about $95 worth. So reason number one to conserve electrical energy is that it's not free. Here's another conservation action challenge here. Go home and look at your power bill. Get your parents to dig it out, get them to get online and take a look at it, and look at how much energy, how much electrical energy your family is using. Okay? And then here's the part of the challenge that I really like. Try to make it go down. Okay, I did this with my family, and it was actually a lot of fun. Believe it or not, I have 2 young kids. I know I look a bit older than that, but I've got a 6- and a 9-year-old. And we would look at our power bill every month, and I would challenge them, okay, let's bring it down, let's bring it down. And we'd look at it together every month. So go home, take a look at it. It's actually kind of interesting. Okay, so let's move on to reason number 2 about why we should care about energy conservation. And this is the important one. This is the really important one. Reason number 2 is that generating electricity uses fossil fuels. Now the fact is that in Saskatchewan we need a lot of electrical energy to power the province. And for the most part we use coal. Okay, we use a fossil fuel. And I want to run through just quickly how that fossil fuel, how coal gets turned into electricity. It's actually not that complicated. Sometimes, by the way, we use gas. We have gas-fired power plants, and in other parts of the country they have nuclear-fired power plants. And actually, a lot of the process is still the same. They just use, for instance, they use nuclear to create the heat. But we'll talk about the coal-fired power plant. I'm going to run through the steps here, starting with coal. So the step number 1 is that we burn coal to get electricity. So we burn the coal. Burning the coal creates heat. Okay. The heat is used to boil water. Eventually that creates steam. The steam rotates a turbine. The turbine rotates a generator, and we create electricity. Phew! That is a lot of effort to create electricity. But that's how it's done. The problem, of course, is that when we burn coal and create heat, something else happens when we burn coal. We create CO2, carbon dioxide. And that's the problem. That's the part of the problem. That's the part of this that I want to talk a little bit more about right now. All that CO2. And you've probably heard a lot about this, CO2 that's being generated. It's not just generated by coal-fired power plants. It's generated by industry, by exhaust fume from cars. There's lots of places that it comes from. And it goes into the atmosphere. Okay? And this is a picture of the planet there, and really the atmosphere covers the whole thing. It's like a blanket that kind of keeps us warm. It actually protects the Earth from getting too cold. But it's really thin. It's really, really thin. In fact, if you look closely, you can see this blue line here. That blue line. And that blue line, our atmosphere, is only about 100 kilometers thick. Relative to the size of the Earth, that's really, really thin. And in fact, as we go up from the Earth, up towards space, most of the atmosphere is at around the 10 or 11 kilometer point. Okay? Because as we go up, the atmosphere gets thinner and thinner and thinner. Okay, so at this level, it's called sea level or 1 atmosphere. Okay, so we're used to this pressure. But as you go up, like if you climb a mountain or something like that, it gets thinner, it gets harder to breathe, and you keep going up, it gets thinner and thinner. By the time you get to the 100-kilometer mark, there's no atmosphere anymore. Okay, you're into space. Now that photograph was actually taken just a couple of months ago by this guy. I always have trouble pronouncing his name. I think it's Kjell Lindgren. He's an astronaut. He's on the space station. And he took this photograph on November 29th, and he said, a remarkably thin blue line protects us from the inky emptiness of space. And he's right. It really is a very, very thin layer, the atmosphere. Just a very thin layer that covers the Earth. Now the Earth isn't actually that big. I don't think it's that big relative to everything in space. Okay, we think it's big, but really 12,742 kilometers in diameter, I don't think that's that big. And it got me wondering about, so if the Earth isn't really that big relative to everything in space, well, the atmosphere must be even tinier because it's just this thin layer that covers the Earth. And I started wondering, what happened? What would it happen if I peeled off all of the atmosphere and put it in a container of its own? How big would that container be? So I started thinking about this, and I got some professors at the U of R and at the University of Saskatchewan to kind of help me with the calculation. And the idea was if we peeled off all of the atmosphere and we put it in its own container, its own sphere, its own atmosphere, if you will, and we equalized the pressure of that sphere so that it was at the same pressure that we're used to, how big would that be? Well, it turns out it would be that big. 2,000 kilometers in diameter. It's really not that big. It's really not that big. And if we compare it to Saskatchewan, it's that big. So when we think of the atmosphere here in Saskatchewan, we need to think of a sphere that's only that big. And the problem is that every year, every single year, that's not going to stay. There we go. Every single year, we're pumping CO2 into that tiny little space. In fact, we're pumping over 30 gigatons of CO2. That's 30 billion tons of CO2 into a 2,000 kilometer diameter sphere. That's a problem. That's a problem. And we're doing it every year, and it's causing things like global warming, it's causing the acidification of the ocean, it's causing all kinds of problems, air pollution problems. So this is why we have to do something about it. Now this can seem a little overwhelming, it can seem a little scary even, but there's good news. The good news is that we are taking conservation actions. Globally, we're taking conservation actions, and provincially, we're taking conservation actions. So one of them is that we're stopping CO2 from entering the atmosphere. Okay? Now, as I mentioned earlier, we need to burn coal in Saskatchewan in order to create enough electricity for us all. Okay? That's going to change. I'll get into that in a little bit. But in the meantime, we're still burning this coal, and it's producing the CO2, and we're putting it in the atmosphere. So one of the actions that we're taking, Sask Power has taken, is they've built something called a carbon capture and storage plant. So at the Boundary Dam Power Station, they've built this and attached it to the exhaust pipes of one of the big generators there, and they're taking out the CO2. Okay, they're still burning coal, but after they burn the coal, they're trying to limit the amount of CO2 that's entering the atmosphere. Now, right now, it's working at about 40 or 45%, which is better than nothing. And over time, they're hoping it gets up to about 90%. So there's an action that's being taken by our own government to limit the amount of CO2 that's getting in the atmosphere. That's great. The second conservation action is, well, don't produce CO2 in the first place. Okay? And we've actually made a commitment, the government's made a commitment that by 2030, 50% of Saskatchewan's energy will be renewable. In other words, we'll start using different kinds of techniques to generate energy. Renewable methods like using the wind. Now, we've already added some wind turbines, but in order for us to get 50% renewable by 2030, we're going to have to add more, and we're going to have to do other things as well. I want to talk about the wind turbine for just a moment. We looked at the coal power plant before. So now I want to look at how a wind turbine works, because in some respects it's kind of similar, except instead of starting with burning coal, we start with the wind blowing. And it rotates a turbine. So remember, when we were burning coal, we actually had rotating a turbine down the list of things that we did, but this way we just use the wind to do it instead of using steam to rotate the turbine. That rotates a generator, and we generate electricity. The great thing is that nothing had to be burned for this to happen. The wind blew, and we used that to turn a turbine and a generator, and we created electricity. I have to say my favorite form of electricity generation is something called PV solar. Photovoltaic. PV stands for photovoltaic solar. And this is a photograph of my garage, actually. And this is one of my family's acts of energy conservation. We installed these solar panels about 13 months ago. And this is what's called a 6.75 kilowatt system. So if the sun is just right, I can generate pretty close to 7,000 watts of electricity. I want to take a look, since we've seen how a coal power plant works and we've seen how a wind turbine works, I want to talk about how a PV solar array works. So we start this time with the sun shining, and oh, there we have it. That's about it. Sun shines, and you create electricity. Nothing burns, nothing moves, actually. It's pretty cool. It's pretty cool. The sun shines, we create electricity. Now, we've had our system for about 13 months, and I want to just show you some of the results. I printed this off yesterday, so this is pretty much up to the moment here. I want to take a look at the results. So since we've had it, so 13 months, we've generated over 8.4 megawatt hours of electrical energy. That's about 8,400 kilowatt hours of electrical energy. Or I like to say it like this: over 8,400,000 watt hours of electricity, which is pretty cool. I'm pretty proud of that. But the really important thing is this. We have saved over 3.3 metric tons of CO2 from getting in the atmosphere by having our solar system. Okay, that's over 3,300 kilograms of CO2 that we've prevented from getting into the atmosphere. So we're pretty pumped about that, and my family, my kids have been involved, and we've looked at our energy bills, and we've turned all of our lights over to LEDs, and we keep an eye on how much electricity we're generating as well. So I'll just wrap up here. I want you to think about three things, okay, as you go forward. And again, I really want to encourage you to participate in the 25 acts of energy conservation. And when you do, think about this. Think about the most sensible way to use energy. The whole concept of efficiency is not doing things that aren't necessary. So if you want light, don't use technology that's more suited to making toast. You know what I mean? So it's interesting to me that the easiest way to do something is often the most efficient. Second thing, learn the language of energy. It takes a while to understand what a kilowatt hour is. You know, you have to sort of think it through. But it's actually fun. Once you learn about that, and especially if you get a watt meter and you start kind of measuring how much energy or how much electricity different appliances use, and you maybe even do some energy schematics and think that through. It's like, well, where's the energy going? It's changing from electrical energy into other forms. What would that be? When you learn the language of energy, all of this becomes more interesting, more fun. And the last thing I want to leave you with is this. You can make a difference. Don't ever let anyone tell you you can't make a difference. If we let ourselves think about energy differently, and if we learn the language of energy, and if we start taking action that makes sense, I think you'd be surprised at how easy it really is to make a difference. Okay, thanks very much. That's all I've got to present, but I will take any questions if you've got any. Yes.
What do you do when it rains in your house? Like, what do you do with the solar panels? Do you put a cover or something?
Okay, so the question is, what do we do when it rains? I like this question a lot because a lot of people ask this question. So a couple of things about our solar system is that we are connected to the grid. Okay, so I'm not off the grid. We're connected to the grid. So if it's dark or if it's raining or if the sun's just not shining, we're not producing electrical energy. We can get it from Sask Power. Okay. However, if it's a really sunny day, like in the summer, and we're not using very much electricity at all, so we're generating more electricity than we can use, then we get credited for that. That goes into the grid, and we get credited. And the way that we designed our system is to be what's called net zero. Okay, so over the course of a year, we are generating pretty much the same amount of electricity that we're using, right? So even though we might need more around now in the wintertime, we're not generating as much electrical energy. We generated more in the summertime when we got credited for that. Okay, so we're using up those credits and a little bit more than that. The other thing I want to point out about if it rains is this. It's a fair thing to say that with solar power and even wind power, that's an intermittent power. You can't really count on it being there. The thing about coal power is you light the fire, you burn the coal, you create steam, you turn the turbine, and it's pretty much there when you need it. With solar power and wind, you don't have that same predictability. So that's one of the biggest issues right now. It's like, how do we make it more predictable? Well, the answer is, I think, fairly straightforward, actually. And I'm going to use your question about rain as an example. So let me ask you this. How many people have taps at home? You turn on a tap and water comes out. Okay, we all do, right? We're very fortunate in Canada. We have running water. That's great. Does it work even when it's not raining? Of course it does. Of course we have water in our taps even when it's not raining. Why? Well, because we stored it. Right? When it was raining and when the snow melted and so on, we stored it and we kept it so that we have it when we need it. Well, I like to think of electricity and the problem with solar and wind providing intermittent power in the same way. It's like, okay, well, it's not always raining, so we don't always have water when we're turning the taps on, or we don't have water outside when we're turning the taps on. Well, the same thing happens if the sun is shining and we're not using that electricity, we should store it, right? And the storage for electricity is a battery. So right now, there's a lot of work being done on improving the technology of batteries so that we can store that energy so that we can use it when we need it. And so that's what's going to be really exciting in the next 10 years or so. We're going to see all kinds of new innovations with both production and storage of energy. Any other questions?
Are there some things that we have no idea to change when we say environmental things?
Can you say that again?
Like, they say power plant. Like, is there anything like that we cannot change yet?
The question is there anything that we can't change to something better? It's a bit of a broad question. I'm pretty much of the opinion that the challenge for us in the next 10 or 15 years isn't actually so much of a technological challenge. My personal opinion is that most of the technology that we need to solve the problem of reducing the amount of CO2 and of creating our own energy and so on, most of the technology we need, we actually have, and it's on track to getting better. Okay, where we need to be innovative and optimistic, I think, is really with governments and policymakers and the people who are deciding how we're going to do this. The reality is we have to shift away from using fossil fuels. We have to. Okay, and everyone's pretty much agreed on that globally. I mean, you probably heard about the Paris Agreement, the big meeting in Paris at the beginning of December. And the thing about that meeting was that everyone kind of agreed. It's like, yeah, we have to do stuff. And then all the representatives have gone back to their jurisdictions. We've had Catherine McKenna come back to Canada and our team. And we need to make the adjustments in order for us to stop using the fossil fuels. the technology that we need to move to, solar, wind, other forms of renewable energy, are kind of there. Some of them aren't working super well just yet. So for instance, my solar system, I bought it just over a year ago. That system that I bought operates at about 20 to 25% efficiency in terms of the solar panels, converting that light energy into electrical energy. Since then, it's already improved by about 5%. Okay, and the cost has come down. That's the other thing, is the cost of photovoltaic solar has been coming down really dramatically in the last 10 years. So I tend to be kind of optimistic about this. I think there's lots to be hopeful for. And the challenge is going to be not so much creating new technology and things that we'd never thought of. It's really about applying the things that we already know about in massive levels. Okay. And in order for us to do that, we need our government and other policymakers to kind of see, well, okay, we need to change the way we do things.